Hi, welcome to Module 3. This is part 3 of the video, and we're going to pick up where we left off, where we were looking at the maps, and there had just talking about variation of temperatures. And I just want you to notice this simple factor of over land, the colder temperatures tend to dip down more southward in the January months, so towards the equator more, and over water, they don't. So the freezing temperature is way up here, and that has to do with the reflectivity and the ability of that item to maintain heat energy. And we call that specific heat. So the Earth's surface has a specific heat, a low specific heat, where it doesn't take much to heat it up. And once it is heated up, it shares that heat energy very quickly. On the other hand, the water as a liquid has a very high specific heat, so it takes a while to heat it up, but once it has that heat energy, it actually holds on to it a lot longer. And this is important because it's going to influence things like how heat energy will react, creating microclimates or climates in situ in particular locations. That also brings me to the reflectivity of these items. So the Earth's surface is something that's not going to be very highly reflective. It's something that will be absorbing a lot more heat energy. So albedo, which is the reflectivity measurements of the Earth's surface, which tends to have darker color regimes, will actually be something closer to 0 on my 0 to 1 scale because it's not very reflective. Where the water surface, especially dependent on the angle that I'm hitting the sunlight at, that will actually have a greater reflectivity, so closer to 1 on its reflectiveness on the surface of the Earth. That also brings me to things that happen to be the same. So for example, if I have the same material, it happens to be like a white shirt. They are both cotton shirts. Color does matter in this regard because it has to do with how much of the visible spectrum will be absorbed and how much of the visible spectrum will be reflected. So if I have a cotton shirt and the cotton shirt happens to be white, that means that the entire visible spectrum of light, all of Roy G. Biv, the entire rainbow, has to be rejected or reflected to have my eyes see that color be white. It's bouncing off the entire visible spectrum. On the other hand, if that shirt that happens to be cotton is black, I am seeing black because the entire visible spectrum, all the way the colors of the rainbow again, is actually being absorbed by that cotton t-shirt, and that's why my eyes are perceiving it as black. So that makes it a black body. Now, as far as albedo scale of those reflectivity of the item, the black t-shirt will be less reflective, closer to 0 on my scale, having an albedo closer to 0, where my white cotton t-shirt will have an albedo closer to 1, meaning it's highly reflective in its set. And I'm just reviewing this because these are key things, and I need you to know them and understand them so that when we move forward in this course, I can say these terms and they will have meaning to you, and we can just move forward. If I have to keep reviewing the terms, the subject matter itself will get lost in its set. So now after reviewing those terms, another key thing that we want to keep in mind is that elevation matters. The higher I go up in altitude in the surface layer of our atmosphere, so we're talking about stuff that's near the surface itself, making it the troposphere on its set. So the troposphere, the one that's closest to the surface, it has a tendency to cool off in temperature as I increase in height. That means that as I increase in altitude and elevation on the surface of the Earth, I will see a decrease in temperature. And this has to do with the amount of sunlight that is received in these locations, the amount of air molecules present in these locations. And there's a couple other microclimate things that I'm about to get into in like 2 slides. So we're going there. So as I increase in altitude or elevation, doesn't matter which one, I am decreasing in temperature. This brings me to what I like to consider microclimates or in situ weather taking place in place of a location. And these things are based on specific areas of the world. So, contrast between land and water. And these are slides with terms and definitions. Please take your time and look through them. I'm actually going to flick to an image that I'm going to use to explain the contrasting or microclimate of land versus water. All right, so land versus water. Let's all go to the beach. So we're on the beach, and the sand, being something that happens to be earth material and therefore has a very good ability at absorbing heat energy, but it doesn't have good specific heat capacity, so it can't hold that heat. It has very low specific heat capacity, so it can't hold the heat in very long, which means it's going to warm up quick when the sunlight's hitting it, and then it's going to radiate it off. So think of every time you've gone to the beach and burnt your little toesies, right? That had to be because the sun was warming the sand heated itself up, and then it started sharing that heat energy, and you burnt your little tootsies, right? On the other hand, the water takes a lot more energy to heat up. And so all of the sunlight that's hitting the water, well, some of it's getting reflected back because it has a higher albedo, and some of it is getting absorbed, but it's taking a long time, and it takes a lot of heat energy to actually heat up water, and that's because it has a high specific heat capacity. It has the capacity to hold heat longer, and it requires more heat to do so, which means that I create a variation in the amount of air molecules in both locations. So all the air that's directly over the sand is in contact with the sand, and the sand is sharing its heat, so those air molecules are moving farther and faster, and they're vibrating quicker, and therefore they're less dense, and they do that lovely thing where they rise, because we're talking about those convection cells we just reviewed, right? So those air molecules are rising, and that creates what a term we call low pressure, right? Less air molecules in that location, therefore I would measure it as having lower pressure, less of them. On the other hand, over the surface of the Earth itself, on the water side, those little air molecules that are bumping up against the water aren't getting any heat energy. So they're kind of cold, they're vibrating a little slower, and so they're kind of compact in that area. They're all compact on themselves, and they're sticking together. Now they're getting very squished. And right over here, there's a whole lot of space. And so they do what anything does when it is squished. It moves to the place with more space, and it rushes to that location, and this causes a natural sea breeze. So that's why when you go to the beach in the afternoon, you'll notice there's a nice breeze coming off the water. So when you look at the water, it blows your hair out of your face, and you get that refreshing breeze of the summer sun, right? And that's because I have a natural high pressure over the water, and wind always flows from high pressure to low pressure because it's just flowing from a place with less space to a place with more space, right? The air molecules are just filling space. So it's flowing naturally from high pressure to low pressure. And this causes what we call sea breeze. Wind currents are all named after where they're coming from. The wind is coming from the ocean, therefore we call it sea breeze, right? So high pressure over the water surface flowing towards the sand. Now, the opposite will happen at night, though. So for everybody who's been at the beach at night, you get all dialed up and you're like, let's go for a walk on the beach. And you go for a walk on the beach and you try to look at the water, and the wind just kind of blows your hair all over your face, and you're eating your hair, and it's just terrible, right? And that's because we have what's called land breeze occur. And that has to do with the fact that that sand and all that heat energy that was down here was sharing all day long, and it was under low pressure, so it was just floating up and away. And so all the air molecules in this location are getting condensed and packed in on themselves. On the other hand, everything over the water took all day to heat up. It was heating up all day long. And now there's a little variation in temperature, and so the water's like, okay, I'll share some of my heat with you little air molecules on the surface. And so it does. And this allows for a natural little warming up, which creates a density variation again, and the warm air rises, right? Low pressure, and it goes up, and that creates a place of space. And so all of the air at night runs from the land to the ocean. And these are microclimates. This is a natural thing. If you live by the water, you know that you get a sea breeze during the day and a land breeze at night. And this is a natural weather condition that you know is going to happen as long as there's no bigger weather condition to come in and interrupt it, like a storm. So now I'm going to pick up with another microclimate that has to do with mountains.